It's a real pleasure to be here. I'd never been to Indonesia before, and this is my first time in Indonesia, and it's a wonderful place. It's a little bit different to Edinburgh. This is a picture of Edinburgh. This is the Edinburgh Castle, and it's what you see when you come out of the train station at Edinburgh. This is the kind of picture you see with the beautiful sky. Usually it's not raining too much. What I'm going to tell you today about is the work that we've been doing over the last 10 years or so, looking at macrocyclic chemistry, in particular these Pac-Man style macrocycles. This is one of my pictures. There's a Pac-Man there. So this is great. I've been taking lots of photos of this. Okay, that's not working. Let me. What happened there? Right, good. So Edinburgh is part of the United Kingdom for the moment. Next year we're going to have a vote. Scottish people, I'm an honorary Scottish person. We will have a vote to see if we want to separate from the rest of England. Here's the border here, and there's going to be lots of high explosive placed. There's going to be a big bang, and then Edinburgh and Scotland will float off into the distance and go further north. So, well, it's an exciting time to be Scottish. Here's another picture of Edinburgh. So this is on a place called Carlton Hill. Here's the castle again. So this is a medieval city, or this part is a medieval city. Very, very picturesque, beautiful city. It's known as Athens of the North because there are some Athens-type follies on top of this hill here. And this is what you can do when you're in Scotland. You can go skiing. It's not very good, but it's okay. And there's lots of castles. So this is a castle on the west coast of Scotland. This is Eileen Donnan Castle that looks out over a nice loch. This is a traditional Scottish outfit. So here you have the kilt. I've worn a kilt before. It's very invigorating. And here's a piper as well. So the pipers are always good when they're on their own. When there's lots of them, it's too loud and very, very noisy. And here's Edinburgh Castle again. Okay, so let's talk a bit about science, and I want to talk about how chemistry can fit into sustainability, and we're talking about sustainable energy, sustainable practices. It's very important at the moment, and it's a grand challenge of the 21st century for a chemist. And you can think about energy efficiency. A lot of what I'm going to say here is from this great publication, this great paper by Lewis and Nacera, who talked a lot about and determined what would happen when energy consumption rises, how much CO2 would be emitted. So we go from 24 gigatons per year to 40 gigatons per year, and what the possible effects of that is. Can we use more energy efficient power systems like fuel cells? And I know there's lots of fuel cell chemistry going on here as well. There's a great book here as well by David Mackay called Sustainable Energy Without the Hot Air, where he balances the energy that we use against the energy that we can gain from using sustainable sources. And you should have a look at this. Go online. It's all online if you want it. You can have a look at that. And what you'll notice is that the energy that we can get using sustainable energy sources is nowhere near that we actually use. So we still need to use fossil fuel sources. We can think about nuclear energy, and this is something that the UK is thinking about quite a lot at the moment. But we require an enormous construction period if we're going to supply this energy using nuclear energy. And of course there are issues with nuclear energy. Uranium is limited. It's only about 100 years worth of uranium in the world. You can think about thorium. And then of course there's the pollution aspects. And I'll talk a little bit about chemistry of the F elements. This is probably the most promising area if we want to think about sustainable energy in any way, and that's to use things like solar, wind and wave power. So these are intermittent. So the sun only shines for half a day, and usually it's shining when we don't want to use that energy. We want to use the energy at night. So you have to think about storage, so capturing this energy in storage. develop more highly efficient photovoltaics. Splitting water into oxygen and hydrogen, so this is what happens in photosynthesis. So can we use sunlight, solar energy to split water into oxygen and hydrogen, i.e. convert it into a chemical energy? And that's a great aim. And hydrogen storage as well. If we're producing hydrogen, how do you store it? Something so we can keep on using fossil fuels is to think about carbon capture and capturing carbon dioxide. But that's an energy intensive process. It uses about 25% of a power plant. So you're using more energy to capture the carbon dioxide. So can we transform this carbon dioxide into something that's valuable, like a fuel? So I'll talk a little bit about that. Lots of us use metals in our chemistry. These are actually critical resources. Metals like the rare earth metals, they're primarily produced in China. So there's a lot of political machinations going on about the supply of rare earth metals. Can we actually carry out urban mining? So we've all got mobile phones. Did you know your mobile phone contains more gold than, a higher concentration of gold in your mobile phone than actually in the ore? Okay, so if you can use or collect all your mobile phones together and extract out the gold, that's a much more efficient way than actually extracting it from the ore. Okay, I think this is where chemistry comes in. So chemistry is really important when we're talking about sustainability. It has a grand role to play in this grand challenge. So what I want to focus on in this talk is some small molecule redox chemistry. And it will become apparent why I'm doing this. And the molecules that I'm interested in are small, and these are the types of conversions that I want to carry out. So I want to think about oxygen reduction to water. So this is the 4-electron, 4-proton process that occurs at the cathode of a fuel cell, and it also occurs when you breathe. People's cytochrome C oxidase carries out this process. The reverse is water oxidation. Can we oxidize water to oxygen and then produce protons? The protons can then go around a reverse fuel cell to produce hydrogen. Carbon dioxide chemistry, reductions to things like methanol, and I'll talk a bit about that, and these other ones as well, but I'm not going to talk about. So let's just focus on water oxidation. So this is a conversion of water to oxygen. This is what occurs in a leaf, and central to that reaction is the catalytic center. This is the oxygen involving center or oxygen involving catalyst of the enzyme photosystem 2. It's a manganese cubane. It has a calcium at one edge, and this is the kind of reaction that is thought to occur where you end up forming an oxygen-oxygen bond by a reaction of this calcium hydroxide with this manganese oxide. So photosystem 2 is a tremendously difficult enzyme to study. It's very, very complex. So what lots of chemists want to do is actually think about how you can mimic these really complex enzymes, make them simple, and then transpose that into an industrial framework. And so you can think about this edge here, the important part, this calcium, oxygen, manganese part of the oxygen evolving center. And you can see that the calcium and the manganese are spaced in, are well spaced, are defined in space. And so can you actually make molecules that can do this as well? So define the space between the two metals. And here's a ligand construct, and this is where the Pac-Man comes in. And this is a ligand that's been used by people like Coleman and Nacera and Chang. And what they have done is taken two porphyrins, so the coordination geometry of the metal is really well defined, and then link the two porphyrins together by something that's rigid, and so you get a really defined space, and the space in between the two metals is very different to the space, the chemical space outside of the cleft. And so that makes it a very, very unique reaction environment, a bit like Mike Ward's unique reaction environments in these cavities. These have been shown to catalyze transformations of small molecules, so these kinds of transformations. But there's a real problem with the synthesis and stability. The synthesis, 15 steps to make one of these, lots of column chromatography, very, very small yields. So when we were looking at this problem, we didn't want to go there, because I like nice, simple ligand syntheses. Okay, so they're called Pac-Man because of this game. And you can see you get 200 points every time when you follow this. And Pac-Man everywhere, it's just here, it's just here. So this is the 1980s arcade game. If you look at the Mimas Moon, using an infrared satellite, then you can see we have another Pac-Man who's just about to eat this dot here. That's a Husseini satellite, that's satelliting Saturn. And then if you think about Star Wars as well, this is the Death Star, here's another Pac-Man here, it's in reverse, and you see it's there. So it's everywhere, so you can use this as a concept. So we didn't want to make porphyrins, but we wanted to use the properties of the pyrrole as a coordinating ligand. And the other properties we wanted to use to try and build up ligands very straightforwardly is shift-based condensation reactions. Because shift-based condensation reactions can give you great control over the macromolecules that you make. So here's our starting point. And you can see this is a bit like a porphyrin, but not quite. So you have two pyrroles, but instead of being conjugated, as you would expect in a porphyrin, you have this sp3 hybridized carbon here that's derived from a ketone. So if you take a ketone and pyrrole, acid condensation, you make this dipyromethane, then you can quite easily, using standard porphyrin type chemistry, tack on these aldehyde groups. And so you can use this compound, which is straightforward to make, and carry out an acid catalyzed condensation with diamines. And the diamines that we used were aromatic diamines, and that was important. So acid catalyzed condensation, and then treat it with base, and you end up with these macrocycles in very, very high yields. They're very easy to make. You can make them in a bucket if you wished. We use glassware because it's a bit cleaner. But we make these usually about 40 grams at a time. What you see is we have two pockets, N4 donor pockets for binding two metals. These two donor pockets are now separated by these rigid aromatics, and we can play around with the substituents on the back and in this meso position. And the key is when you actually metallate, you end up going from a flat macrocycle to a folded macrocycle. So here we've metallated using palladium, so we've deprotonated twice. This is palladium in its 2+ oxidation state, therefore a square planar. And you end up with this folded structure, so the chemical space in between the two metals is very different to that which is outside. They're very structurally rigid, and this is where the Pac-Man motif, because it's going to bite down on what's on the inside. We can change the properties of these compounds by changing either the meso positions, the substituents on the meso positions. So if you put bulky groups on, it tends to open up the mouth of the Pac-Man and make it twist a bit. So it kind of chews instead. And you can change the hinge. So if you put a much larger aromatic hinge in, you separate out the two metal compartments. So here are the two macrocycles, and I'll talk a little bit about the chemistry of these. So here we have a fluorinyl group, that's our bulky group, and we have this diamino, or this macrocycle derived from diamino anthracene. So let's just talk about catalysis and reduction of oxygen. So this is a 4 proton reduction reaction, so your catalyst has to manage 4 electrons and 4 protons. It occurs in fuel cells, and so it's important if we want to have a very clean way of generating energy. And we made 3 different compounds. So these are cobalt compounds, they're derived from cobalt-2. So here's a cobalt Pac-Man compound, and you can see this is now cobalt-3 and cobalt-3, and we have a peroxo sitting in the middle. Okay? So this was good because this is the first time that anyone had managed to crystallize a cobalt Pac-Man compound that actually had a reduced form of oxygen in between the two metals. If you change from the dimethyl meso substituents to this fluorinyl meso substituent, you change the chemistry and you favor this superoxide cation. And here's the anion here. This is a hydroxide that's hydrogen bonded to the superoxide group that's sitting in between the two metals. And if you change again and you go for the macrocycle in which the two compartments are now really well spaced out, you can isolate compounds like this. This is a cobalt-3 aqua hydroxy complex. So this is a hydroxy group bound through this hydrogen bond to water. And so all of these compounds are potential intermediates in the catalytic cycle of the reduction of oxygen to water. Think about the catalysis now. They actually work as dioxin reduction catalysts, and the way we monitored this was to use ferrocene as our electron source. And when you provide electrons using ferrocene, you generate the ferrocenium ion, and therefore you can monitor that using UV-vis spectrophotometry, because that one's blue. And if you have a limited amount of oxygen, you can determine how much water or peroxide you're generating in that reaction. Okay, so here we have the concentration of ferrocenium, and if it's a 4-electron process, we expect the line to be up here at about 6.8 millimolar. And we can see from our first catalyst, which is our first generation complex, this is a really rubbish catalyst. But if we change to the fluoronyl substituent catalyst, then we can see that if we increase the concentration of catalyst and the acid, and we follow that line, it progresses to about 600 seconds to the 4-electron reduction. So it's there, but it's slow. But then if we then change the catalyst again to where we've now spaced out the two compartments significantly, you see we get very rapid 4-electron catalysis. So this is actually a very, very good catalyst for the 4-electron reduction of oxygen to water. So at the moment we're looking at these compounds to see if we can actually incorporate them into membrane electrode devices and see if we can then make fuel cells. Let me now think about water oxidation. So this is the reverse process. And if you want to think about water oxidation, well, maybe you can think about biology. And here again is the oxygen evolving center of photosystem 2. And we've already said it's a cubane. Schweiger's made this manganese oxocubane and showed that it's effective for carrying out this reaction. Agapai recently made a calcium manganese oxide cubane and used ligand design to build up the complex. So you've got this, this aromatic, trigonal aromatic ligand. You can install the manganeses first and then cap this off with calcium. Okay, so this is a really, really nice result. This came out in Science in about 2010. You don't need to use manganese. You can use more expensive metals like ruthenium. And Tony Lobet in Spain has been using these ruthenium complexes and shown that this particular complex has activity that's very similar to photosystem 2. Very, very rapid conversion of water into oxygen. You can use Pac-Man compounds. Naruto, some 20 years ago now, showed that this dimanganese Pac-Man compound was an effective catalyst for water oxidation, but only when you used an oxygen-containing chemical oxidant. And we made this compound in 2007. This is a dimanganese Pac-Man compound. This is manganese 2, manganese 3 with a hydroxide in the middle. But we haven't tested that for oxygen evolution chemistry. And generally, bimetallic manganese compounds will not carry out this reaction. You need to have more than 3 manganeses in your compound. So we thought we'd look at magnesium chemistry. And it will become apparent why I'm talking about this in a minute. You can make the Pac-Man compound. So this is a magnesium 2 Pac-Man compound, and it has THF sitting inside the cleft and outside the cleft. What we found was that when this was hydrolyzed, and you can see this was a mistake initially, we had some trace amounts of water in our reactions, but if you hydrolyze it stoichiometrically in benzene, you get a precipitate of this new compound here, which is a magnesium hydroxide cubane that's been encapsulated by the macrocycle. So there's this in the middle, this group, this is a magnesium hydroxide cubane, which is a new cluster for magnesium hydroxide. It decomposes slightly if you leave it in air, but if you make sure there's no air around, there's not any more water, then you don't get any decomposition. So what's happening here is something that's meant to happen, or is very similar to what's meant to happen in the oxygen evolving center in photosystem 2, in which the protein of photosystem 2 controls the aggregation of the manganese oxide cubane in photosystem 2. What we've done here is by using these macrocyclic ligands, they control the aggregation of this magnesium hydroxide cubane by enveloping the cubane motif. let's think about this a bit harder, and you can see that the bonding of the macrocycle is different now. This is the asymmetric unit. You can see that we have this bowl shape now, this bowl-shaped macrocycle, and it's only bound to the magnesium through these imine nitrogens. And the pyrroles are now protonated and hydrogen bonding to the ancillary ligands. And so this hydrogen bonding motif is important as well in stabilizing this whole complex. These are called tennis ball structures because the way that the two macrocycles wrap around the central cubane looks a bit like a tennis ball, and that's very similar to some work by Rebeck. So can we make manganese calcium cubanes? Well, we don't know yet, and this is unpublished work where we've taken now the Pac-Man macrocycle and we've shown that we can make these calcium compounds as well. And you can see they form bowls as well. They don't form your standard Pac-Man. It's this bowl-shaped motif. This one is particularly exciting where we only have one calcium because we now have space to put more metals in, and we're going to try and build up extra manganeses into this pocket. Okay, so now I want you to shift your head a bit. And we're going to talk about nuclear chemistry. This is why nuclear chemistry is a challenge. This is plutonium. This is what goes into nuclear bombs. This is what it does. This normally, it just self-heats. It glows. So if you have a lump of plutonium, it will glow. This is what happens when you have some kind of disaster. Cesium-137 is a volatile, and so you can see how cesium-137 spread around Europe after the Chernobyl incident. And there's a need to understand F-element chemistry, primarily because of nuclear chemistry. And this is what happens when you carry out fission, nuclear fission. You get all of these different products. Effectively, you generate the periodic table. Some of these are quite nasty. Some of these long-lived fission products, you can see they are they are stable for many millions of years. Okay? Here we go. This is 80 million years here for these long-lived fission products. So what you need to do to get rid of these fission products and get rid of the actinides that you're forming, americium and curium, you need to try and put them back into the reactor, and so you need to separate them. And you use chemistry, your chemistry knowledge of these F elements to separate these. So the major component, which is uranium, and uranium in the environment, is this compound here. So this is the uranyl, which is a dioxo of uranium, and it's uranium in its highest oxidation state in +6. So if you think about the rest of the group 6, so we've got tungsten, molybdenum, and chromium, and you can see there's a big difference between this one and these, in that this is trans oxos and these are cis oxos. And then if you think about the reactivity of the oxo groups, chromium dioxo is exceptionally reactive. And this example that I've shown you here, this chromyl difluoride, will react with methane gas. So it activates CH bonds. Molybdenum dioxo compounds are very good at epoxidation, good epoxidation factors. The uranyl oxos are exceptionally inert and are not known to react. Because they don't react, the only chemistry that you generally see are substitution reactions in the equatorial belt. And that's how the Purex process, which is a process that's used in Britain to separate out nuclear fuels, works by using these tributyl phosphate ligands to carry out a solvent extraction process. Okay? So the oxo groups are inert. The other point is that you can carry out redox chemistry on the uranyl, but in aqueous systems, the uranyl 5 is unstable and it disproportionates into U6 and U4. And that's very useful if you want to think about immobilizing uranium, because you can carry out these procedures. So before we carried out any work in this area, there were only very, very few examples of uranium 5, uranyl 5, and there were no oxo group reactivity. So this is work with Polly Arnold at Edinburgh. She happens to be my wife, so it's a great collaboration. And what we did is we took the Pac-Man ligand. You can see we've got these acidic protons, and you can carry out acid-base chemistry to install a uranyl. And you only get one uranyl in, and you end up forming this uranyl Pac-Man compound. So it still folds, and it still ends up at this Pac-Man shape. Now the important thing here is that you still have the ability now to add other elements into this bottom pocket that will then address this oxo group that's sitting in the mouth of the Pac-Man, and we'll leave this one alone. So now we can address one uranyl oxo and see how the chemistry is affected on the other one. And this has given us lots and lots of really good results. So if you take the uranyl Pac-Man and you can treat it with this silyl amide base to deprotonate these NHs and then react with a transition metal salt, you get a really weird reaction. This is something that was completely unexpected. What we've done is we've formed an oxygen to silicon bond, and we've reduced from uranium-6 to uranium-5. So this is the first example of a reductive silylation of the uranyl dication. You can control the reduction by adding different amounts of lithium amides in this case. If you only add one lithium amide, it acts as a base, and you end up with a uranium-6 compound. If you add two, the second lithium amide acts as a reducing agent, you end up with a uranium-5 compound, and I'll go through that a little bit more. You can use lanthanides in their 3+ oxidation state to reduce uranyl to U5. So that's quite unusual, you wouldn't expect that, and it's not actually the lanthanide that's doing it. You're carrying out a bond homolysis, you're homolyzing the lanthanide to nitrogen bond to form these compounds that have interesting magnetochemical properties. And then we recently found out you can actually get 2 uranyls into the Pac-Man, but you have to use forcing conditions. And so if you boil this compound with some extra uranyl silyl amide in pyridine at 120 degrees, then you can form these compounds in which you carry out reduction and silylation. And the other thing to note is that one of the oxos has gone from this cis position to a trans position as well. So we've got the bond rearrangement going on as well. So let me just talk very briefly about the reduction and oxo group silylation. So here's what we wanted to do, and here's what we thought we were going to do. We were going to treat this compound with 2 equivalents of base. Unfortunately, we used this base because it only works like this with this base. We thought we were going to make this compound and then react it with a metal iodide to form this compound here, which would have an oxo to metal bond. But instead, what happened was we got this silylation and formed this compound here. Here's its crystal structure. So what you can see, we've got the uranyl. It's still in this trans-oxo disposition, but now the bonds, the uranium-oxygen bonds, are significantly lengthened to the uranium-6, but not as long as uranium-4. So this is U5. And we've got now this silyl group on this oxo. So that's the first reductive silylation of the oxo, of the uranyl oxo. We thought we'd use lithium amides instead of potassium amides, and we get completely different chemistry, and that's not unusual because lithium is very different to potassium. You treat this compound with one lithium amide, it acts as a base, you end up just deprotonating one of the pyrols to form a new lithium to uranyl oxo bond, but it's diamagnetic. You treat it with 3, you end up with complete deprotonation of the bottom pocket, but also reduction, and you form this paramagnetic uranium-5 uranyl. And then this is the key reaction where you've used 2 lithium amide bases to form the U5. I just want to talk a little bit about the mechanism here. So what we know is that you can electrochemically reduce the uranyl 6 to the uranyl 5 at this redox potential, about -0.5 volt. And if you look at the redox potentials of these lithium bases, or lithium reductants, then you can see they're not really strong enough reductants to carry out this reduction. What Trevor Hayton found was that if you coordinate a Lewis acid to a uranyl oxo, then the reduction potential of the uranyl moves more positive by about 0.6 of a volt. So if this happens, then we should expect lithium amide, this is LDA, lithium diisopropyl amide, to reduce this compound, and we would expect lithium silyl amide not to reduce it. So lithium diisopropyl amide acts as a reducing agent. We end up at deprotonation. The lithium is a Lewis acid. It interacts and changes the redox properties of the U6, and then enabling this reduction to occur, producing an aminal radical which we can identify. With lithium amide, it's not reducing enough. And we actually find that we can generate two equivalents of the byproduct, and this is acting as a base only. And to get to the product cleanly, we have to add a CH bond that has a bond dissociation energy less than 80 kcal/mol, and something like dihydroanthracene will do that. And so we have a CH activation process going on. We're not sure if it's a classical transition metal type H-atom abstraction reaction, or if we're getting some internal reduction through the pyroline. But both ways, you need to invoke this CH activation reaction to get to our end product. So that will tell us how we can do a reduction, but it doesn't tell us how to do a silylation. And this is the mechanism that we put into our Nature paper. It was a bit of guesswork, but we got Laurent Moran to do some calculations. And so our anticipated reaction was that we deprotonated using a potassium base. This activated the uranyl to carry out, in this case, a silyl atom abstraction or a silyl group abstraction to form the oxygen to silicon bond and then reduce the uranium to U5. And then we can finish off the reaction by then doing a substitution reaction with this metal halide. We don't think that's correct now, primarily because we've done a lot more experiments. And we think that what is important is, of course, the activation of the uranyl by binding to a transition metal, in this case to zinc. So zinc is a Lewis acid. We've activated now this U6 to reduction. And when you've activated reduction, this oxo group becomes a lot more Lewis basic, and so can now bind to a second zinc, and we can now get this silyl group radical transfer to transfer the silyl group onto the oxo instead of having the zinc there. So we think this is a transition metal mediated silylation reaction, and we've got other evidence that can hopefully stand up when we try to publish it. Okay, that's my time up. Just a few conclusions. I think chemistry is really important if we want to think about sustainability and the sustainable future. So you're all studying the right kind of thing here. You're thinking about chemistry. Chemistry is really important. Hopefully I've showed you we've got a nice modular synthetic approach to these Pac-Man architectures, and that by using these Pac-Man architectures we can make new catalysts for oxygen reduction. We're also carrying out carbon dioxide reduction chemistry as well. We can use these macrocycles to encapsulate cubanes, and we're now trying to extend that to more classical manganese oxo cubanes. And we've described lots and lots of new fundamental uranyl oxo group chemistry. This is a statue that commemorates the commandos in the UK. So this is in Scotland. This is the Ben Nevis range, which is the highest range in Scotland. And as you can see, lots and lots of snow around. So it's a very, very tough training environment for the commandos. I just want to thank a few people. So this is my current group here, an excellent group of students, and I've had some really, really talented students and postdocs in the past. Collaborations, in particular Professor Polly Arnold, who's my favourite collaborator, and then these other guys as well, in particular the guys at Nottingham where I effectively started this work. Funding is from these people. This is a view of the west coast of Scotland on a nice sunny day, because it's always like that in Scotland. Thank you very much for listening.
Thank you. Now I invite several questions, please. We have this.
Thank you, Dr. Jason Love. So I'm quite interested in defining the catalyst for oxidation of oxygen. You showed us
Oxidation of water or reduction of oxygen?
oxidation of water. So you showed us that catalysis can serve as the catalyst, and also your catalysis. So can you tell us that what kind of requirement that we have to in this catalyst as the circular reaction?
So
The requirement of this catalyst.
for the reduction of oxygen or the oxidation of water?
Reduction.
Reduction of oxygen, right, okay. The requirements are you need a cheap metal, because at the moment the metal used is platinum, which is very expensive. You need something that's going to be thermally stable. The reactions are run in a proton exchange membrane fuel cell. They're run at about 80 degrees or so. And they need to withstand a highly acidic environment as well, because the protons, when they come from, so what effectively you're doing is you're oxidizing hydrogen to form protons. They transfer through a membrane to the cathode, and when they come through the membrane, your acidity is about the same level as triflic acid. So an extremely acidic condition. So the actual catalyst needs to be able to withstand highly strong acid. That could be a problem with these systems, because you can think that it's very easy to protonate the metal from the macrocycle. And so we might need to make stronger coordinating macrocycles. What your catalyst needs to do is coordinate oxygen and then deliver the protons and electrons to it. And so that's the key. You can use porphyrins on their own, but generally they carry out only a 2-electron reduction. So to deliver the 4 electrons, you need to have some kind of assembly that will then coordinate and stabilize all of the intermediates in the reaction. So you go from dioxygen, you form a metal oxo, and then you protonate that metal oxo. And so you need to be able to cycle around using metal redox chemistry. And so you also need metals that are capable of changing their redox chemistry or their oxidation states by at least 2. So that's why it's good to have 2 metals in there, because you can think about the 4 electrons coming from both metals. So there's lots of design aspects that you need to consider, and a lot of that those design aspects come from previous work, which helps.
Yes, one more question.
Yeah. I just want to ask how the application of this catalyst is possible to use this catalyst not only for water or oxygen reactions, but I mean another application, not only focused on oxygen and water only. Like
Yeah, we're also looking at carbon dioxide reduction. The catalyst I showed you, the one with the fluoronyl head group, the bulky head group, does carry out carbon dioxide reduction. But we're not in a position to publish that yet, so I'm not going to say anything further about that, except it works. We haven't carried out any, let's say, you could consider using these catalysts for oxidation reactions, because they're very similar in some respects to the Jacobson catalysts. And also, we haven't really looked at any organic transformations, and that's something that could be interesting. Introducing some chirality into the macrocycle to carry out chiral transformation. But we haven't done that.
Yes, please, sir. Yes.
Yeah, I'm really curious about the stability and the lifetime of the catalyst.
Yeah.
I think this solution must be interesting to analyze, investigate. I think.
Mm-hmm.
So, to your research, how about the stability and lifetimes?
It depends on which particular compound you're looking at.
Oh.
Okay, so the cobalt compounds are generally stable in air, and they're insoluble in water, so they're pretty stable. But then we've made compounds across the whole periodic table. It all depends on which particular metal you're using, which particular macrocycle you're using. Generally, we carry all of our work out in glove boxes and on Schlenk lines, so we don't let any air in, unless we make a mistake and then it does something good, perhaps. So, yes, serendipity is good, but we generally try to make sure that we've got a high level of control over our reaction conditions.
I think we give applause to Professor It's very interesting, and for you